we've already proceeded to prove one of the cases to complete our proof of the Euler's formula. Recall Euler's formula is this combination here, number of vertices minus number of edges plus number of regions in a connected planar graph is equal to 2. And what we had done is looked at the simplest case and then assume that it's true when a graph has n edges, any graph with n edges. And now we're going to proceed to look at a graph with n plus 1 edges, which can be obtained from a graph of n edges by adding either an edge with a vertex, and that's our case 1 that we've already proved, or an edge with no vertices attached to it, and we'll attach that to 2 existing vertices. So that'll be our case 2. So case 2, we'll add an edge with no vertices, but we'll attach it to 2 existing vertices. So the situation that might happen here, for example, is in this graph over here to the right. Maybe we'll take these 2 vertices here and add an edge. We want to maintain planarity, and so if we do that, notice we've split one region into 2. Or perhaps what we do instead is we add those that edge to some vertices that are pendant vertices in the unbounded region. So perhaps we'll add that edge out here. Those are the 2 situations that we can easily conceive of, and if we do that, we've split the unbounded region into 2. Now the same thing, it doesn't have to be that these are pendant by any means. We could get the same result here. If we attach the edge to those 2 vertices, then we still will split the unbounded region into 2 regions. Again, it doesn't have to be pendants. That could have happened if we did it just attaching this vertex to this vertex in the unbounded region. Again, we split it into 2 regions, this one that's now bounded and the one that's out here. So whatever happens in that case there, when we add the edge, we increase the number of regions by 1. So what happens here is when we do that, we get that the number of vertices has not changed. The number of edges has changed by 1. It's the old number of edges in the graph with n edges, plus 1 edge, the one we've added, and the number of regions has increased by 1 as well, because the effect is to split a region. So if we form the expression of number of vertices minus number of edges plus number of regions, notice that we have this same plus 1 in one case. That's where we're subtracting a 1, and we have the plus 1 in this case where we'll be adding it. So in fact, when we complete that computation, we'll simply get the number of old vertices minus the number of old edges plus the number of old regions, because the one that we're subtracting in this term and the one we're adding in this term will cancel, and we'll still get 2. So that completes the induction step, and therefore completes the argument that this will always hold, Euler's formula always hold, in the context of a connected planar graph. Now we're going to use that in a couple of examples. First of all, we're going to just use it along with a specific case where we have a map with 4 degree 3 vertices, 4 degree 4 vertices, and 4 degree 5 vertices. And the question is then, how many regions does it have? The thing that's going to make this work is that, first of all, we can find the number of vertices, right? We have 4 of them here, 4 of them here, and 4 of them here. So that's simply 12. 4 plus 4 plus 4. The number of edges we can find because we know the sum of the degrees of the vertices is twice the number of edges. So what we have is, first of all, the number of vertices is 12, then 2 times the number of edges, is the sum of the degrees of the vertices. It's also the sum of the degrees of the regions in a planar graph, right? But here, this is the one we want because that's 4 times 3. Therefore, with degree 3, that's plus 4 times 4. That's how many that will contribute. Plus 4 times 5, the 4 of degree 5. And taking all of that together, we get 12 plus 16 is 28, plus 20 is 48. Okay, so that means E itself, the number of edges is equal to 48 divided by 2 is 24. And now using Euler's formula, we can find that from V minus the number of vertices minus number of edges plus the number of regions is 2. We can discover that 12 minus 24 plus the number of regions is 2. So the number of regions is equal to 14. Okay, so that's a pretty quick little example, but it illustrates how to use several of the properties together. A nice kind of a problem for an exercise or an exam question. Now, the next thing I want to do is use Euler's formula to get some properties about planarity. And so the next thing we have is a corollary that I want to prove here. This is corollary 3. Corollary 3 says that if G with vertex set V and edge set E is a connected, planar, and simple graph, so it's not only is it connected and planar, it's also simple, so there's no loops or multiple edges. And it has order 3 or more, so at least 3 vertices. Then we have this relationship between the number of edges and the number of vertices that doesn't involve the number of edges at all. And I didn't leave enough room below this to actually prove this, so I'm going to write it above. So I'm going to write what corollary 3 basically says. Corollary 3 says that we have G is connected, planar, and simple. And it has at least 3 vertices. If that's true, then the number of edges is less than or equal to 3 times the number of vertices minus 6. Okay, so that's the thing I want to prove right here. So the key idea here is to use the sum of the degrees of the regions is equal to 2e. So we will use, so the proof, recall the sum of the degrees of the regions, regions ranging over the set of regions, is equal to 2 times the number of edges, like so. Now, in a connected, planar, and simple graph, simple very important here, with at least 3 vertices, the degree of a region will have to be at least 3. So first, the degree of each region is greater than or equal to 3, and the reason is that there's at least 3 vertices and it's connected. So the minimal graph you could have here would be the 2 edges like so, and the only region here is the unbounded region, and the degree of the unbounded region would be, well, figure it out. Take a second, come back after you've paused. The degree of the region, in fact, will be 4 because it has to be a closed graph, a closed walk that we use to count that the degree. So it will have to start one of these points here, 1, 2, it has to be closed, so we have to go back 3 and then 4, going back like so. So the degree is at least 4. Now we can get a region of degree 3, so if I did something similar, again, there's at least 3 vertices, so I could have just 3 edges like that, connecting that, and each of the regions has degree 3. But there's no way to get a degree 2 region, which would result if you had multiple edges like so, but that's disallowed because it's simple. So each region has degree 3 or more, and that means that then 2 times the number of edges equals sum of the degree of the regions are in R, summing over all the regions it's R. It's greater than or equal to summing 3 for every region in the set of regions, that would be 3 times the number of regions. So the sums of the degrees of the regions has to be at least 3 times the number of regions if each has degree 3 or more. So we have this relationship between the number of edges and the number of regions. In other words, I'll turn this around and say the number of regions is less than or equal to 2/3 the number of edges. So in Euler's formula, we have the following. If I rewrite Euler's formula starting with E, then E is equal to the number of vertices plus the number of regions minus 2. Check and make sure that's what it is. In fact, it's still up here, right here. So if you put E on one side, for example, if you took E to the right and subtracted the 2, we would get the number of edges. I should put the bars around that. Is the number of vertices plus the number of regions minus 2. Right, okay. But the number of regions is less than or equal to 2/3 of the number of edges. So if I put 2/3 the number of edges, that's the bigger thing here. It will make this right-hand side bigger, like so. And now if you simply look at the extremes here, this quantity here and this right here, that says that E is less than or equal to that. So let's now subtract 2/3 the number of edges from both sides. That should be an E there. And if we subtract that from over here, we'll be left with 1/3 the number of edges is less than or equal to the number of vertices minus 2. And the final answer then is what we wanted. Multiply through by 3 and we get the number of edges is less than or equal to 3 times the number of vertices minus 6. Multiplying both sides by 3. Now, one of the reasons that we wanted to do this, I will show in the next video.